Colleagues and friends, welcome to this webinar. This is part of the SEAM webinar series. The Surface Engineering for Advanced Materials is sponsored by the Australian Research Council of Australia. This webinar is being given across many time zones. Whether you're having your very early morning coffee, your breakfast coffee, your lunch coffee, your dinner coffee, or your very late evening coffee, welcome. My name is Chris Berndt. I'm Director of SEAM, and it's my distinct pleasure to introduce our very special speaker this morning, this afternoon, this evening, Professor Dr. Rehan Ahmed. Dr. Ahmed is an expert in the tribology of surface coatings. He's the Associate Director of Research in the School of Engineering and Physical Science at the Heriot Watt University in Scotland. He leads a multidisciplinary research in the design of engineering systems with an emphasis on surface engineering of interacting surfaces. He has many roles. He's an associate editor for IET, the Journal of Engineering, and he serves on the editorial boards of the Journal of Thermal Spray Technology and Advances in Mechanical Engineering. It is my distinct pleasure to pass on the floor to Professor Dr. Rehan Ahmed to speak on the tribology of tungsten carbide cobalt coatings in sliding and rolling contacts. Professor Ahmed, the floor is yours.
Dear Chairman, thank you for the kind introduction. And I am grateful to the excellent team at the Surface Engineering for Advanced Materials for inviting me to deliver this webinar. In this webinar, I will be talking about the tribological design considerations of these carbide coatings. And I would also like to say a warm welcome to the attendees in this webinar. So tribology is a multidisciplinary and a fascinating area of research. And it deals with the science and engineering of interacting surfaces in relative motion. And it touches a number of aspects of our society, from the design of artificial human joints to the computer hard disks and the movement of glaciers to the interaction of debris on the solar panels of the space station. So really, really vast and interesting area of research. And just to give you a figure, that almost 23% of the world's energy consumption originates from the tribological context. So this gives you an overview of the vastness of the area of this research. So thermal spraying also is an important segment of surface engineering market, and the global thermal spray coatings market was estimated to be $7.6 billion in 2020, and it is projected to grow at a compound rate of 7% to reach 10.7 billion by 2025. So thermal spray tungsten carbide cobalt coatings are used in a variety of industrial applications to protect against abrasive wear, erosive wear, sliding wear, and fretting fatigue. And some of these applications include impeller shafts, aircraft flap tracks, conveyor screws. And as the science and engineering advances, there is a potential for new applications. Today, I will be concentrating on the sliding wear and rolling wear of these coatings. So just to give you an overview of the webinar, I will be giving a brief introduction about the tribology in sliding contacts and link the coating microstructure with its mechanical and tribological properties. Then I will touch upon the current state of the art in numerical modeling of wear, a short description on the importance of residual stress in these sliding and rolling contacts, and finally, a few slides on mapping of failure modes in rolling contacts. So predicting the sliding wear performance of coatings requires us to understand the complex interdependencies of the wear mechanism. Now, before we embark on full-scale industrial testing of coated components, the cost of development can be significantly reduced using the standard ASTM test procedures. In sliding context, there are three important tests which are used either independently or in combination to understand the wear mechanism and predict the wear rate. In ASTM G133 and G99, as you're seeing on your screen over here, the difference between the two tests lies in the sliding direction. And we have a ball or a pin which is coated with a which is coated, or we could have a specimen which is in the plate or a disc form, and a normal load is applied to it. And the difference, as I said, lies in the direction of sliding, which is unidirectional motion in the ASTM G99, and we have a reciprocating motion in ASTM G133. We also have another test, which is the ASTM G77, also known as the block-on-ring test, as shown here. And in all of these tests, we measure the wear volume using some interferometric or some other scientific techniques. And then we link the normal load and the total sliding distance to measure the wear rate, typically in millimeter cubes per Newton meter. The post-test evaluations of wear track then help us identify the wear mechanisms, and a number of factors are important here, as discussed in my next slide. So in terms of the tribological test conditions, the test method, the test method parameters, material of the counter body, and also the load, the speed, and also the environmental factors. They all play an important role. And the selection of these parameters influence the contact pressure, the formation and removal of tribofilm, which is very important in sliding contacts, and the entrapment of any wear debris within the contact region, because that shifts the wear mechanism from two-body abrasion to three-body abrasion. However, this is only half of the story, because the selection of the coating process, the process parameters, the characteristics of the powder, they all influence the microstructure and thus the mechanical and tribological properties of the coatings. And the combination of the two halves of the diagram indicate the interdependency and complexity of the design parameters. So factors such as the elastic modulus, the hardness and fracture toughness of the coating and ball material, along with the surface chemistry of test couples, including the tribofilm, play an important role. So this slide shows the typical microstructure of the tungsten carbide cobalt coatings deposited by the suspension, which is a nanocomposite high velocity oxyfuel coatings, and also conventional high velocity oxyfuel coatings. And the coating microstructure for all coatings in these cases is dense, both in the aspirate and hot isostatically pressed conditions, which has been shown as hipped over here in all of these cases. In terms of the transmission electron microscopy, the images of the coating shown here for both conventional coatings and also with the nanopowder particles indicate uniformly distributed particles within the coating microstructure, as you can see here, for example, and also for other types of coatings, as you can see here. So the phase composition of conventional high velocity oxyfuel coatings indicate minimum carbon loss, leading to very limited M6C or CO3W3C transformation, as shown in the XRD pattern in this figure. In the case of suspension high velocity oxyfuel coatings, there is a relatively higher carbon loss due to the thermal loading of nanoparticles in the thermal spray coating process. And this leads to both M6C and M12C type of carbides, and also a nanocrystalline hump, as shown here, around the 2 theta of about 35 to 42 degrees. Now, when suspension coatings are heaped at about 920 degrees C over here, the nanocrystalline phase stabilizes, and you cannot see the hump which we saw in the aspirate conditions. And when we compare the XRD pattern of these nanocomposite coatings with that of the vacuum plasma spray coatings, as shown here, you still see the formation of the M6C type of carbides or phase transformations. And that's despite the lack of oxygen in the VPS process. Now, this slide shows how the phase composition is related to the carbon loss. And this is at 1000 degrees Celsius. And at that temperature, W2C does not exist as a stable phase. So you don't see W2C in this diagram. And in fact, we didn't see any W2C in the coatings which were heaped at around 920 degrees Celsius. And the path of the carbon loss from the left of the screen, which is tungsten carbide 12 cobalt, to pure tungsten or elemental tungsten on the right. So as we go from left of the x-axis to the right, it crosses several two-phase and three-phase fields. And the M12C carbide, which is the CO6W6C, appears twice as an equilibrium phase, one for the low carbon content and the other for the higher carbon content. Similarly, a metallic tungsten appears as an equilibrium phase with the higher carbon loss. So all of these characteristics of the microstructure, and when we combine them with the characteristics of the test method in sliding wear, give us information about the failure modes. And the failure modes in these tungsten carbide cobalt coatings can be characterized in 6 main categories. The first one shown over here in caption D is the carbide pullout, where the carbide effectively leaves the coating microstructure. The next one in caption E is carbide fracture, which is transgranular fracture in this case. In caption F, what you're seeing is the preferential removal of the matrix, leading to the exposure of carbides. So you can see some carbides are being exposed because the matrix around them has been removed. Then the importance of tribofilm as seen in the caption G, and you can see small amount of tribofilm form on the surface of the coating material. And in most cases for these coatings, WO3 is the most dominant tribofilm, which reduces both the friction and the wear. So it's quite beneficial to have this tribofilm. Then repeated sliding can lead to subsurface and near surface cracks, leading to the delamination of the coating. And then also the changes in the wear mechanism from 2-body abrasion to 3-body abrasion, as shown in caption J. So these are some of the wear debris collected at the end of the test, and they can cause additional wear due to the 3-body abrasion. So this is just an overview or summary of the 6 different categories or types of wear mechanism which dictate the overall performance of the coatings. Then we can look at the counterbody itself, which is a ball or a pin in this case, and the changes in the contact area as shown here. You have a wear in caption A of the counterbody, which can lead to a reduction in the contact pressure. You can also have some tribofilm formation on the surface of the counterbody, and also some abrasive marks as shown in the caption C over here. So this was a quick overview of the failure modes in sliding wear. One of the factors which influence the preferential matrix erosion and fracture of grains is the carbide mean size. And this slide shows the effect of average carbide size on the binder mean free path. And a reduction in the binder mean free path is expected to improve the wear performance. And we will see in the next few slides how the average carbide size affects the tribomechanical properties of these coatings. In this slide, the average carbide size on the fracture toughness is plotted, and other literature also indicate similar values of fracture toughness for these coatings. Now, theoretically speaking, a reduction in the carbide size should increase the fracture toughness, but we do not see this behavior over here because we can see as the carbide size is decreasing, so is the fracture toughness. And that is because of the complexity of the coating microstructure. And this slide also shows the inherent anisotropy in the coating microstructure, leading to relatively high values of fracture toughness perpendicular to the coating surface and relatively low values, as shown by the red line in the graph, when we are measuring the fracture toughness parallel to the surface. In terms of the measurement of the fracture toughness, if we have nice crack pattern as shown here propagating from the edge of the indentation diagonal, we can use various mathematical relationships. For example, a couple of them are shown here to evaluate the values or the experimentally measured values of fracture toughness of K1C. However, in practice, when measuring the indentation fracture toughness, the crack pattern is complex, which includes both the radial cracks as well as other cracks around the indentation, as shown by the red and the yellow arrows. And in such situations, acoustic emission technique provide a useful solution when dealing with a complex crack pattern, as shown by the schematic of the acoustic emission setup. So in the acoustic emission technique, the cracks are associated with a sink-in zone, also some radial cracks, and also some edge cracks, as shown in the figure. And a mathematical treatment of the energy of the acoustic emission signal and crack lengths can be used to evaluate the fracture toughness in these complex cases. The technique can be applied to a range of coating materials. As you can see here, we have applied it to both tungsten carbide cobalt as well as some aluminum oxide coatings. And it also gives you a low bound and a high bound value of fracture toughness, depending upon what parameters you are using to measure the fracture toughness. Let's have a look at some of the structure property relationship. And in this slide, the Vickers hardness is plotted against the average carbide size. And there's a trend here that the increase in the tungsten carbide retention leads to an increase in the Vickers hardness. And this is different to what we saw in the case of fracture toughness in the previous slides. And there is a trend of increase in Vickers hardness with a decrease in average carbide size, as shown by the green arrow. Now, this slide shows the influence of the carbide size on the sliding wear rate. So we have the sliding wear rate on the y-axis and the average carbide size on the x-axis here. And given the complex interdependency of the coating microstructure and test methods for sliding wear, it is not possible to get a general relationship between the carbide size and the wear rate. There is, however, a trend of increase in the wear rate with the increased presence of M6C and M12C phases, as shown for the APS coatings in the circles. So in this slide, all the circles are effectively for the APS coatings. Similarly, we can look at the effect of sliding velocity and coating heat treatment on the sliding wear performance. And the slide shows that the wear rate can be improved with the coating heat treatment under certain tribological conditions. Similarly, the sliding velocity can have a significant influence on the wear rate. We can plot similar diagrams and analysis based on the influence of the normal load, the type of the counterbody, the test duration, the test parameters, and come up with some sort of relationship. However, all of these relationships are not as well defined. As you can see in the next slide, where we're trying to formulate a semi-empirical mathematical relationship between the wear rate and mechanical properties, and this requires us to have an understanding of the failure mode. So in the first graph, you have coefficient of friction and product of coefficient of friction against contact pressure plotted against the wear rate. And what you're seeing here on the top is that on the legend of the figure, you have the counterbody, which is aluminum oxide or tungsten silicon nitride or tungsten carbide, and similarly HV and PL represent what type of coating process was used for that particular investigation. We can try other relationships. For example, the one on the bottom here, we have a contact pressure, a combination of the coating and ball hardness, coefficient of friction, and velocity. And we can't get a very good general relationship using these techniques. But we do get an envelope of the wear rate as a low bound and high bound values. Similarly, if we try and plot the Vickers hardness against the wear rate, or a combination of the ratio of the ball to coating hardness and contact pressure against the wear rate, we don't get a very well defined relationship. However, once we include all the factors, such as the ball and the coating hardness, the fracture toughness, which is very important in these cases, the contact pressure, we begin to see some sort of trend. So we have used a combination of these factors on, as you can see on the x-axis, we have the ball and coating hardness, we've got the elastic modulus of the ball and the fracture toughness of the coating and some contact pressure, and plotted against the wear rate in this case. We begin to see some sort of trends forming. However, the trend is still not well defined. And the reason it is not well defined is we need to look at the wear rate itself. You see, the wear rate has a force term in it. As you can see, it's got a Newton over there. And this alludes the wear performance as the influence of a given load is geometry dependent. For example, a load of 25 Newton on a steel ball of 10 millimeter diameter is not the same as a load of 25 Newton on a tungsten carbide or an aluminum oxide ball in terms of the contact pressure. Even for the same ball material and dimensions, as the load changes, the contact pressure changes non-linearly. Hence, we can include the influence of geometry in the wear rate calculation, or we're going to redefine the way we calculate the wear rate by replacing the force component, shown over here, with contact pressure or Hertzian contact pressure. And once we do that, we can begin to differentiate the wear rates as shown in the next slide. So here we have replaced the normal load with contact pressure in the wear rate equation, and you can see that some trends are being formed, both for high velocity oxyfuel, conventional and nanocomposite coating, as well as the plasma spray coatings. And we can use similar relationships to calculate the semi-empirical relationships between the wear rate and the test parameters and the coating microstructure. So this gives us a quick summary of the semi-empirical mathematical treatment of the sliding wear, linking the coating microstructure with the wear rates. Now, having looked at the sliding wear rate, I'm going to talk a little bit about the importance of residual stress. Now, the relationship of wear rate in previous slide do not include the residual stress in the coating material. And the magnitude of residual stress can be significant, and it can also be advantageous in combating coating fracture. For example, compressive residual stress can prohibit mode 1 crack initiation and propagation, whereas a tensile residual stress can be detrimental to the coating performance. So in this slide, there is a compressive residual stress of 300 megapascals, which can be advantageous. However, too high value of compressive residual stress is also not beneficial for the coating. The measurement of residual stress itself is quite sensitive to the measurement technique. So that's the other factor which you need to consider when you are looking at the incorporation of residual stress in the sliding wear or rolling wear performance. So in the next slide, I have plotted a tungsten carbide with 10 nickel chrome. So it's not a tungsten carbide with cobalt matrix, but I included this because it gives a very nice back-to-back comparison of the two different measurement techniques, one of the non-destructive neutron diffraction and the other one of destructive hole drilling technique. And as you can see that there are some differences in the measured results, and the difference between the results lie in the type of stress being measured. Hence, care need to be taken when superimposing the residual stress field under sliding or rolling contexts. We can also model thermally the residual stress generation in thermally sprayed coatings using copper, Eulerian, Lagrangian finite element methods. We can do it with single splats and with multiple splats. And this video shows a single splat impacting on a substrate using a thermally coupled Eulerian Lagrangian finite element model. And once the coating builds up, you can look at the evolution of the residual stress in the coating material. Now, having looked at the experimental evaluation and mathematical modeling of wear rate in previous slides, I'm going to talk a little bit about the numerical modeling of the wear rate. The numerical modeling is still in its infancy when it comes to sliding wear. However, these models can provide some useful prediction of the wear rate. And there are two approaches which can be adopted to model sliding wear in finite element method. The mesh deletion method, as shown here. So we start with an original mesh. Then we define some sort of criteria in the model to suggest that these elements have failed based on our criteria, as shown by the red elements in our mesh. And then we delete those elements and form two new surfaces. And these new two surfaces will be the surface of the worn part in that particular technique. The second approach is to model the wear rate using the movement of the surface nodes. So let's assume that these are some surface nodes which are going to form part of the contact zone during sliding wear. And as the body wears, the surface node basically adjust down. So these nodes, which I drew earlier on, have now moved to this location over here. And the adjustment of the nodes give us the volume, as shown here in the shaded area, of the worn material. So both approaches can be applied. And I'm just going to show you some results in the next slide of how the approach works. Now, the numerical modeling of sliding wear in tungsten carbide cobalt coatings have not yet been successfully attempted. This slide shows, however, a comparison of the experimental and numerical results of the technique for various values of KD. Now, KD over here represents the wear coefficient which is used in the model. And although the model is for stellite 6, it shows the application of the modeling approach. And there is a reasonable agreement between the experimental and the numerical values for particular values or particular value of KD. However, as I said, these models are still in their infancy because these models rely heavily on the experimental data and cannot be created without it. The approach can therefore also be applied to thermal spray coatings, and the SEM image of the actual alloy for which this was modeled is shown here, and you can see that it's got two different phases, which are carbides as shown over here, and also some matrix shown over here in this particular region. The other consideration in the numerical modeling of wear is the microstructural phase itself. As you saw in the previous slide, we had a carbide phase and the matrix phase. And generally, the microstructural phases are not individually considered when modeling the wear rate. And the overall material behavior is used for modeling of in the finite element. However, we can model the matrix and the carbide phases separately. And this particular video, the second video which you're seeing now, shows how the carbides in the microstructure can be included. And this is an elastic plastic nano scratch model where we are increasing the load linearly. And this approach can then be used or coupled with the Wearate numerical model I showed you in the previous slide to improve the accuracy of the sliding wear results. And you can see in the figure over here, the oval shaped surfaces over here, which you're seeing, the geometry effectively is an approximation of the carbides in the nano scratch test in this particular case. So finally, I would like to talk a little bit about rolling contacts. Now, rolling contacts are fundamentally different from sliding contacts in a number of ways. And the first thing which is important here to note is that in sliding contacts, which we have been looking at up until now, for pure sliding situations, the maximum shear stress because of the coefficient of friction or high coefficient of friction is always on the surface. So the interacting surfaces between the coating and the ball always have the residual, the maximum shear stress on the surface. When we go to pure rolling conditions, the maximum shear stress shift subsurface is no longer on the surface, and it is effectively sitting subsurface as shown here. And the image on the right of your screen, as you can see over here, shows that the maximum shear stress has shifted subsurface for both the ball surface and the coating surface. Now, rolling contact fatigue tests can be performed using a modified ASTM standard as shown here. And in this test configuration, the coated specimen, so we can have either a coated cone or a ball or a plate as shown here, but in this illustration, I'm using a coated cone. And it rotates against the three planetary balls. So it drives the three planetary balls over here until the specimen fails. And these tests are usually performed in lubricated conditions. And now there are two important pieces of information which we get from these tests. Number one, the rolling contact fatigue life in terms of the number of stress cycles to failure. And number two, the failure modes of the coating in rolling contacts using the post-test evaluations. The friction coefficient in rolling contacts is generally an order of magnitude lower than sliding wear. So you're looking at a friction coefficient of 0.03 or 0.05, some similar number. Now, in terms of the actual failure modes in rolling contacts, they can be defined in four main categories as abrasion, delamination, bulk failure, and spalling. And the SCM observations over here show some images of the failed areas. In the caption A, you can see some micro pitting within wear track, which led to the failure of the coating. The second image is that of a delamination within the coating, which is in this particular case, the delamination within the coating material at the depth of maximum shear stress, but you can also have delamination at the coating substrate interface. You also have the migration or the bulk failure where the substrate plastically deforms and don't have the ability to support the coating under the contact pressure. Or you can have a typical spall, which you also see in conventional rolling element bearing and gear materials. However, if you design the coatings with care, you can actually design them to withstand about 70 million stress cycles as shown here. So that's the wear track and that's the width of the wear track. And the coating after 70 million stress cycle is shown here. And the reason we're using 70 million stress cycles is because that's one of the industry standards for these type of tests. So once we have got the information about the failure mode and the design parameters such as the contact pressure, the yield strength of the substrate, the coating thickness, and the depth of maximum shear stress, we can use that to design the coatings. And this is shown here in this map, which is a non-dimensional map. And we have non-dimensionalized the x-axis in this map. So where the coating thickness has been non-dimensionalized by the depth of maximum shear stress. And also on the y-axis, we have non-dimensionalized the contact pressure with the yield strength of the substrate. And if we draw these maps, we can map out the different failures, but also the areas where we are likely to get a reasonably high value of the fatigue life cycles. And the lubrication regime in this particular case is shown as the secondary x-axis. And here the full lubrication regime means that there is no asperity contact between the ball and the coating surface. So these two surfaces are completely separated by the lubrication provided in the test. We then also can identify the areas which we need to avoid. So the red rectangle and the blue rectangle is the area which need to be avoided because that's more likely to lead to the failure of the coatings. So this concludes my presentation, and in summary, it is possible to predict sliding wear rate based on the structure property relationship. However, further developments to incorporate the role of microstructural phases and full-scale testing residual stress still need to be incorporated. Numerical modeling of sliding wear is an emerging area and can help with the design process, and contact failure modes can be optimized for coating performance. Finally, I would like to thank my research team and collaborations, and I'm grateful for the support of the present and past research members, research councils for funding, and the academic and industrial partners in this research. Thank you very much for listening, and I hope that you find it useful. This concludes my presentation, and I will now pass the mic back to the chairman.
Thank you very much, Professor. That was an absolutely fantastic talk. I'm voiceless, almost. And I'll be using this talk as an example to all colleagues, including students, about how to convey so much information so nicely, so wisely, so well delivered. I want to indicate to the audience that there is still some time to ask some questions. I would also like to indicate to the audience that this presentation will appear at some time within a week or so on the SEAM website. And I'd like to encourage you all to speak directly, Professor Rehan Ahmed, if you feel that there are some areas where you'd like to collaborate with him. So, Professor, are you ready for some questions?
Yes, please.
Okay, so let me try to start. What is the best value to indicate wear resistance of tungsten carbide cobalt coatings? Is it hardness, fracture toughness, or maybe a combination of both, or maybe something different? What is the best value to indicate wear resistance?
I think from the literature and from the experimental work which we have done over the last number of years, I think the combination of factors as shown on the x-axis of the slide over here normally gives the best results, because most of these results are not just our own work, but we have put them based on the published literature as well. Now, we would like to populate more in terms of the references here. I just would like to add. And the problem which we are facing is that a lot of published literature in this particular area do not quote the values of fracture toughness, which makes it very difficult. But the references which we could find normally yield that the x-axis of this graph is a good start for that particular mathematical relationship.
Okay, so this comes on to the next question. You did mention fracture toughness. So in your opinion, what is the best method for measuring fracture toughness of these coatings?
I think that still the indentation technique works well because the technique basically allows it, because the coatings are generally thin, and we don't want the measurement of fracture toughness to be affected by the substrate properties. So the indentation fracture toughness normally is a better way, in my opinion, to measure the fracture toughness. However, we do end up with complex crack pattern as shown over here, and the mathematical relationships as we have at the moment are not able to deal with the complex crack pattern over here. So that's why we embarked on the use of acoustic emission technique, where we basically calculated the total crack lengths and different types of cracks and related that to the measured fracture toughness. And we were able to, in this particular case, as I did mention aluminum oxide here, this was very difficult for us to measure using conventional indentation technique. But with the acoustic emission technique, we were able to get some answers in that. And I think this particular paper, and there are others as well, please have a look at the reference quoted here, and it will hopefully guide you in some of the practices of measuring fracture toughness in these cases.
Well, let's move on to wear testing, please. There is an issue with regards to wear testing and reproducibility of results. So in your experience, when one carries out a wear test, this person would like to know, would like to look at your experience with regards to the reproducibility and how many wear tests should be carried out for any material.
I think that before we embark on the full-scale testing, a minimum of 5 tests would be a good start in terms of reproducibility. But that also depends on the test parameters which you're using for the test which you are using, because as the load increases, the mode of failure in the coatings can change, and you may have to look at the failure mode, because one of the things, I mean, measurement of the wear rate is an important outcome of the test, but I think the understanding parts come from the understanding of the failure modes. And if you're having a big scatter in the test, then maybe the best place to look at is the failure modes to try and understand why is there so much variation in the results. But in my experience, I think 5 to 7 tests maximum normally would be significant enough in a particular condition to get a satisfactory value of the wear rate.
I have a very interesting question and commentary from one of your former students at Heriot University. Do you remember Mr. Mohammed Tarek? Mr. Tarek is now at University of New South Wales, and he comments that he is very happy and he loved your inspiration. And for that reason, for better or worse, he is now at University of New South Wales. But now his question.
Well,
so one of your former students. My question is,
Tarek, yes.
I
didn't know, Chris.
Are the mathematical and simulation models in tribology nowadays accurate enough that we can use them to influence the simultaneous shape and material design when designing materials? In other words, does finite element modeling have any practical use for real engineers who design structures?
I think in terms of the general use of finite element modeling, it is a very, very useful tool. However, when we are using the finite element model to look at the sliding wear performance, the models are still in their infancy. But this is how things start with a lot of research. We have to work around the problems or the challenges, which also are the opportunities. And I can relate it to the question before, because we talked about the variability of the experimental data. And I think that is one of the things which affect the finite element modeling, because the finite element modeling results are heavily dependent on the semi-empirical experimental data, which is used as a modeling approach. So it has a future, but we still need to come some of the challenges, because in the design process, we are moving everything using computer simulations and trying to reduce the cost of the development of a product. And in that regard, finite element analysis is a very, very useful tool.
Okay, so here's a very practical question from Dr. Surinder Singh. He wants to improve the sliding wear resistance of a gang circular saw blade, 0.5 meter in diameter. A blade 0.5 meter in diameter. Is it possible to coat the saw blade with about 1.8 millimeters thickness the blade is 1.8 millimeters in thickness. Is it possible to coat that 100 micrometers on both sides by HVOF to avoid bending of the blade? Let me paraphrase. Can thermal spray be used to help the support of this blade by coating it on both sides, in your opinion?
I think given the dimensions of the blade, Chris, I mean, there is no doubt that we can coat the blade. There is no problem with that. But I am just thinking aloud here in terms of the application. If you're trying to resist the bending in the blade, then there will be some stresses which will be developed at the substrate of the coating and at the interface of the coating and substrate material. And that may lead to premature delamination, like in a conventional fatigue type of failure. I mean, that's what I can think about at the moment, but without looking at the actual application. But what you can use the coating for is to improve the life of the blade in terms of the wear and tear of the blade. So the number of times you replace a blade after X number of operations, it might improve if you try a coating material on the cutting edge of the blade.
It would not surprise me, Professor, if Dr. Singh engaged you one-on-one to discuss this.
I look forward to that. Thank you.
I have 3 questions which are kind of the same. Residual stress and wear rate, the fatigue performance, phase contribution to residual stress. So residual stress and its influence on the wear rate, residual stress and its effect on fatigue performance, and residual stress and how that changes phases, if at all. 3 different questions from 3 different people.
Chris, I'm not getting the question very clearly, but I'll try and answer from what I could understand. In the mathematical relationship which we use, there is no residual stress component, but it is a good idea to measure the profile, which is the through thickness profile of the residual stress. In sliding wear applications, the residual stress very near to the surface is important. So if you don't have access to neutron diffraction or other techniques, you can use a conventional X-ray or synchrotron type of technique, because that will give you a value of residual stress near the surface. You see, problem with tungsten carbide is that it's so the atomic weight is such that the conventional X-rays do not penetrate more than 3 to 4 microns, even when you're coming vertical from the surface. Yeah. So that's why we move to synchrotron, to the neutron diffraction. So that may be sufficient for sliding wear, but when you're looking at the rolling wear type of things, you really need to understand the through thickness profile, because without it, it will be very difficult to design the coating, because you see there is a sharp in terms of the actual interface where the coating and the substrate meet. There's a sharp change in residual stress, and that can cause issues if it is not understood properly. Okay. But the other thing was we haven't incorporated them into any sort of modeling of wear rate at the moment. Okay. What we do know is that
I think we've got time for 3 questions more.
Okay.
You showed that at low velocities, the wear rate was higher. So therefore, what is the best velocity? How do you determine the velocity?
Chris, the velocity will normally depend upon the application, because when you're looking, I mean, these, as I said, before we move on to the full scale testing, we need to conduct a number of tests at different velocities just to see the effect. And the thing which is changing when we are changing the velocity is, first of all, the flash temperature, which is the temperature at the asperity level. As you go higher, you're putting more energy into it, and that affects the formation and removal of the tribofilm. The other thing is the actual stress, the actual role of wear debris, because at lower velocities, it may be that the wear debris gets entrapped within the wear track. And at sliding velocity, as you increase it slightly, you have a much clearer path in front of the counter body moving, and the entrapped debris basically does not affect the failure mode in that particular case. So this was a slide which I put on just to show you that how sensitive the measurements are, and you really have to understand the way you design the coating and what the application is, because just doing the test and getting some data out isn't sufficient. It's the knowledge behind it which is the critical part.
Okay, Professor Milan would like you to address dissolution of tungsten carbide by the matrix during thermal spraying. Can you briefly address the dissolution of tungsten carbide within the matrix?
I think that's a very good question. And when we were looking at the nanocomposite suspension coatings, we tried different things. We have tried, and if you look at the literature as well, including ourselves, we've tried to coat the tungsten carbide particles with a cobalt matrix. And similarly, you can try and optimize the coating process parameters. You can look in suspension springs, especially, you can look at different ways to cool the coating, because as I said, there was an interesting slide on the VPS and suspension comparison. And even in VPS, you have M6C carbides forming. So it's more of a function of temperature than oxygen, and that these eta phases are formed. So I think if you can control the thermal loading and somehow protect the particles, maybe by providing a layer of cobalt or some other material around it, it just makes the processor a little bit more expensive, but possible.
Okay, so we've got time for 2 questions. We started a few minutes late, so we'll end a few minutes late as well. So Professor Peter is asking about a very interesting question. Here it is. Is anyone using the lubricant to self-repair the coatings during wear? Is anyone actually putting something, incorporating some species in the lubricant to enable self-repair?
It's a very good question, and I mean, in the time I had, I didn't have the time available to look into these kind of things. In terms of lubrication, yes, there are some studies where people have, or researchers have, incorporated the solid lubricants such as the molybdenum dioxide or some similar materials within the coating microstructure to improve with the friction and wear performance of these coatings. I would also like to add that when you're doing tests under lubricated conditions, not solid lubricants, but conventional lubricated conditions, the porosity generally plays a positive role rather than the negative role, because the pores in the coating sometimes act as reservoirs within the sliding contact, and it can improve the sliding wear performance. So yes, it is possible to add solid lubricants within the coating material. And sorry, I didn't have time to look into that in my presentation because of the time constraints.
So there are further questions coming in. So unfortunately, I can only ask one more. And then you'll be able to relax just a little bit. Can you please detail the process for constructing the contact fatigue wear map? The contact fatigue wear map. How did you do that?
Okay, so it took us almost 3 years to develop a map of this nature. And so it says a number of tests using the design of experiments where we are going to be varying the contact pressure, the yield strength of the substrate, and the coating thickness. Because one of the things which you could look at is that this particular area over here, sorry, my pen's just not working. Over here, you can see that, Chris. You have a much higher range in terms of contact pressure which you can apply, but it's also related to the coating thickness, because as you go from the right to the left, in this particular case, the coating thickness is lower and lower. So we are shifting all the shear and orthogonal shear stresses into the substrate. The downside of that is that if the stress changes, and because as the stress will change, the subsurface shear stress will move more towards the surface. And as we do that, the failure is more likely to migrate into this area. So it's a design of experiments to look at different parameters in this map, especially the 4, which are the X and the Y axes. We originally will fix the lubrication regime to full regime in these kind of tests. So we are not looking into that in the initial phases. And then we conduct some tests in mixed lubrication regime just to indicate that if there's a breakdown of lubricant film, what happens in the failures, basically. Okay. So, and after the test, it's a lot of work in terms of identifying the failure modes, some finite element modeling, and residual stress work, and some crack, because we have to use techniques to identify the cracks which were subsurface and not surfaced as yet, but the coating failure has already started. So a combination of post-experimental techniques, design of experiments to come up with a map of this nature.
Okay. I'm really wondering whether I can squeeze you for one more question. Okay, thank you for being so agreeable, Professor.
You're welcome.
Dr. Taylor, this is the very last question, would like to indicate that he'd like to ask a question about whether the tungsten carbide cobalt chrome coatings can be replaced with iron-based amorphous coatings. So we've talked a lot about tungsten carbide cobalt, but there are new generation coatings on the market, amorphous coatings. Can you please convey your opinion on the basis of your experience about whether this is on the near term, current or long-term horizon?
I think that all new technologies or all new applications into this area need to be carefully considered. And I cannot talk specifically about those coatings without the data in front of me, but I think it's worth looking into those things, because as we have seen that even for the suspension high velocity oxyfuel coatings, which have a relatively higher carbon loss, for example, in our case, they still outperform conventional tungsten carbide coatings under certain test conditions. So it's not just about the coating itself, it's about the application or the test conditions as well, because a coating may perform well under one condition and not the other. So, but certainly in terms of new coating developments and using amorphous coatings, it's an area which is exciting and should be looked at.
Okay, so what I'd like to do now is draw this webinar to a close. I'd again like to indicate that this has been supported, that this webinar has been supported by SEAM, Surface Engineering for Advanced Materials. I'd like to compliment and congratulate Professor Rehan Ahmed on an absolutely wonderful, informative, professional presentation, which has clearly been a lot of thought has been put into this information, which has been transferred around the globe. And if you do have any further questions, or if you feel that you'd like to enter into a collaboration with the professor or with SEAM, then of course that is one of the objectives of this SEAM webinar series. So what I'd like to do now is thank everyone from around the globe, from whatever time zone you are in. I'd like to thank you all for joining this webinar and now close it down. Thank you very much, sir.
Thank you very much, Chris, and all the audience, and wonderful questions. And I hope that you found the presentation useful, and I look forward to hearing from those who are interested in some collaborations and future work. Thank you, Chris.